diffraction.
Thank you very much for the kind introduction. I really appreciate that. And I would like to thank the organizers and especially Esther for doing their great work and for allowing me to speak. So I'll be talking about the work which is done in collaboration with Pavel Lazarev, who actually represents two companies. ESDX works on hardware and performs some experiments, which I'll be talking about. And Mature UK is actually built to analyze the obtained data. So from very beginning, from the discovery of X-rays, it was used for medicine purposes. But all these applications are based on the absorption of X-rays. However, there is another effect, X-ray diffraction, which is discovered a little later, but it contributed a lot to our knowledge of the crystal structure. And a little later, again, it was discovered that it's possible to crystallize biological molecules. And how it's done, biomolecules are crystallized, and after that, X-ray diffraction is measured. And from this diffraction, the electron structure is resolved, and we have the structure of our molecule in atomic level. And it led to enormous number of Nobel Prizes. And for example, famous double helix structure of DNA and corresponding Nobel Prize was based on X-ray diffraction works by Rosalind Franklin. But this is not what we are doing. We do not crystallize biological molecules. We just use X-ray diffraction on biological tissues without any crystallization. And to distinguish ourselves from biocrystallography, we introduced the term VitaCrystallography, which is what we are doing. Okay, so what is our motivation? We want to address the status of extracellular matrix. The space between the cells is not empty. It plays a lot of different roles, and specifically, there is electrical signal between the cells, and also the immune system actually works in this space. There is a lot of components of extracellular matrix with certain periodicities. And the status of this periodicities, status of the structure, can be monitored by X-ray diffraction. So how it's done? We have our sample, and we have X-rays going through the sample and scattered. Now, if we have certain periodicity D in our structure, there is corresponding momentum transfer Q, which is just 2 pi n over D. And this is allowed momentum transfer between incoming and outgoing X-ray wave. Because if we have fixed periodicity, we have fixed magnitude of our momentum transfer. And because X-ray scattering is elastic, in this diagram, you can see that magnitude of momentum transfer dictates the scattering angle to theta. However, we don't have perfect crystal, and instead of certain points in our diffraction pattern, azimuthal angle is arbitrary, and we have a ring, which can be seen here. And if we integrate over the angle, we would have dependence on the intensity on the momentum transfer, so-called scattering profile. And there are two ranges of scattering profiles, so-called small angle X-ray scattering SACS from 0.1 to 5 inverse nanometers, and wide angle from 3 to 60 inverse nanometers. Our prototype diffractometer actually covers from 0.7 to 58, so we cover both SACS and wax regions. So this is typical scattering profile of healthy breast tissue. So we have inverse q to the 4th power dependence from the amorphous scattering and specific peaks from certain components of extracellular matrix. Many orders of magnitude from the collagen. Peak at 1.5 inverse nanometers related to the packing of fatty acids in triglycerides. Fatty acids themselves would give contribution to the peak at 14 inverse nanometers, and peak at 20 is related to the oxygen-oxygen distance in tetrahedral structure of the water. So this is what we can get from this type of materials in healthy breast tissue. In another tissues, we have different molecules, for example, keratin, and keratin can have a preferential direction. So instead of circle, we have certain features which are called eyes or arcs related to the distance between molecules and the dimer and pitch in the helix of these molecules. Okay, so why now? Because before all these experiments were done in synchrotrons, and it's impossible to put synchrotron in a medical office. Now we can prepare a tabletop prototype, which is quite small and relatively inexpensive. Also, there is a progress in digital detectors, which are much better than the photoplastines used before by Rosalind Franklin, for example. And of course, there is a huge progress in computation power, because right now we can store enormous amount of data and we can examine them. So we have several prototypes, 3 of them based on copper, and they are located in our California lab at Ulster University in Northern Ireland and in Queen Mary University in London. And the penetration depth of copper-based is quite small. For molybdenum is larger. We have one prototype at Ulster University, and also we have a prototype based on silver, based in our California lab, and using this prototype, we can measure in vivo patients. I'll be talking about that later. If we have some doubts about our results, we can bring our samples in synchrotrons. So we have collaboration with the Diamond synchrotron in the UK and DAISY synchrotron in Germany. Okay, now what was observed? We have striking difference between healthy and cancerous tissues in these diffraction patterns. So this peak at 14 is very pronounced at healthy, and is suppressed in comparison to the water peak for the cancerous samples. In SAX region, we have triglyceride peak completely disappearing in cancerous tissues. So it's related to the lipid metabolism in the presence of tumor, and this is our main direction of examination. However, of course, these are ideal cases. Most patients are somewhere in between these two, so we need to perform machine learning. And I would like to introduce several metrics for machine learning without many details. One of them is sensitivity. It shows how accurate our identification of pathological samples. If it's 1, it's perfect, more than 0.1 excellent, and more than 0.8 very good. Specificity shows how accurate our identification of the healthy samples with the same range of values. And balance accuracy, it's 1/2 of sensitivity and specificity. And also so-called area under the receiver operating characteristic curve. It shows how the clusters of healthy and unhealthy samples are mixed in the space, for example, of principal components. Okay, so we have several projects. We study human samples, we study animal models, we study small biopsy samples to work with within the pathological lab. We're working toward the in vivo applications, and quite important thing is we are trying to establish the remote cancer detection using proxy organs, nails and skin. And what I'll be talking about is a recently published paper unpublished results, and just everyday based updates, because some of figures are really updated on everyday basis. So for a pathological lab, we collaborate with a famous pathologist, Professor Louis Jones from Queen Mary University. So the goal is the following. Histopathology analysis of a single sample requires several days of work. However, 80% of biopsy samples return to be healthy. So we need some kind of triage system to identify which samples should be addressed first, because they are malignant, and any delay can be fatal for our patient, and which samples can wait for a couple of days. So Biobank, directed by Professor Jones, supplied samples from 305 patients, some cancers, some non-cancers, healthy and various benign lesions, which were analyzed. So these are metrics for direct binary cancer, non-cancer analysis. And they're not that good, mainly because we don't know what means healthy. Because healthy samples obtained from the risk reduction patients, and we don't know if they're really healthy. And also we have all types of benign samples which should be differentiated. So we followed specific task, distinguishing between healthy and, cancerous and benign for the pathological lab, and we had excellent separation. But in these benign samples, we cannot include fibroadenoma, because this analysis is based on lipids, and lipid response of fibroadenoma and cancer is very similar. So we addressed that, examining the collagen and water response, and obtain again good separation. And water is just structured by the collagen, and if there is anomalies in collagen scaffold, it can be seen in water signal. Next, animal models. We used the following experiment. The left lobe of the mouse was inoculated with cancer cells, and mice were sacrificed in specific days to establish the cancer trajectory. So it can be seen because cancerous cells were, some luminous molecules were introduced in cancerous cells, so we can follow the progress of tumor. And these are our results. You see the evolution of this signal from the left inoculated lobe, from the healthy to unhealthy shape. For right lobe, no change in the shape. And actually, this gives us several very important conclusions. All these results previously were obtained for human breast tissue. We saw exactly the same for the prostate tissue of mice, which means that we have a similarity between the organs. We have the similarity between different species. And also quite important that the symmetry can be a diagnostic tool which will be used later. Next project, the same story, but cancer introduced not in prostate, but in mammary gland. And also we have cancer trajectory for left breast and quite less trajectory for the right breast. And now we can introduce this symmetry as diagnostic tool. So we can compare our signal from the left and from the right breasts of the mice. And for example, from the left breast of cancerous mice to the left breast of healthy mice. And the ratio of the peaks at 14 for lipid and 20 for water is our figure of merit. So this is for early stages, days from 6 to 10. Clusters are mixed. And this is for later days when cancer is established. Now we have almost full separation of clusters with some outliers here. So symmetry again is very, very important tool for this sense. Next, we examine the skin of these mice. Skin contains collagen and fat, and the lipid signal, again, was different for the days as a tumor established. We did not believe ourselves initially, because we did not see the changes in the right prostate, but we did changes in the skin. We sent our samples in synchrotron and obtained the same results. And this is a physiological consequence, because if we have paired organs, and if one is affected, the second one should work as long as possible. But skin is connected by the blood channels to all the organs, so it can be affected. Next, nails. We used the nails from the dogs, and again, with the known diagnosis, we compared cancerous and non-cancerous samples. They are quite different. We can separate them and obtain the very good metrics. So from the nail of the dog, we can tell if this dog has cancer or not. The same story with the mice. We have all the organs from our sacrificed mice, so we can compare the signal from cancerous and healthy mice. So this feature is not that pronounced as the dogs, because the nail is smaller, but still we have cancer trajectory. And again, this is up to day 5 yet, but it's already we have already this area under the curve larger than 0.9. We continue to measure them, and eventually we compare the nails from prostate cancer and nails from breast cancer, that maybe we can distinguish between them. Next, of course, we want to check if we can do the same with the human nails. And we collected cancerous hospital in Kazakhstan and healthy nails from our own hands, and send them to synchrotron. These are results. And again, the measurements were done in April. So we have just preliminary analysis, and we have the separation between cancerous and healthy nails in humans. And finally, this is our apparatus in the hospital in California. This is Byron Aram, our chief medical officer. We measured 325 patients. Results are not that good in direct sense, because for biopsy, we have the same size for all the samples. For patients, the size of the samples are completely different for different people. So we used the symmetry approach, because for the single person, the size is almost the same. So when we can compare the signals from the left and right breast, and the metrics improved significantly. And after that, we can actually combine these two approaches, direct measurement and symmetry, and improve it even more. And also quite important parameter is specificity at 0.95 sensitivity, which means if we quite good in the determination of cancer, how many patients can go home. And this is 0.47, so 47 of 100 can go home without, for example, taking a biopsy. So there are several other developments. We have a classification of human pancreatic biopsy samples. It's we are preparing a paper on that. We need to do multi-class classification, various grades and cancer types. We need to actually examine if other pathologies, not cancer, can lead to the changes. And for example, quite important, we need to account for the age, because the healthy profile can change with the age. We can examine the brain tissues. Again, this is a poster by Lev Murokh here. what I really want to do myself is to perform quantum chemistry computation to determine the form factor for X-ray diffraction scattering. So to compare that to the experimental data and to see exactly what changes in the structure led to the change in diffraction pattern. And in general can be extended to many different quality control projects, for example, control of artificial cotton, wool, silk, and so on. So these are my conclusions, that we revealed several structural biomarkers which can be used for early diagnostics of pathologies. These biomarkers are similar across different organs and different species. In pathological labs, we can use that as a triage system to fast-track potential malignant cases, and we are working to develop in vivo prototypes to eliminate unnecessary biopsies and rapidly screen healthy patients. Using proxy organs such nail and skin, actually, we can revolutionize the diagnostics. Now, a couple of words of the funding. Funding in the US is supplied by private people, and in the UK, we have several grants from Innovate UK. And this is a list of people working on this project. Thank you very much.